So this section is on orbits and gravity. We'll talk a lot about the beginnings of the science. Science is really, most Western people believe that credit science is beginning with Galileo, but it's much more complicated than that. Galileo lived from 1564 to 1642, and and that's roughly the time people think science began. He gets a lot of credit for the scientific method and some discoveries. Other people will say science began in 1543 in a particular year, which is kind of silly. But the reason they pick that year is because Copernicus's book, which we talked about in the last chapter, and another book called Human Anatomy by Andreas Vesalius, both came out in that year. And Vesalius's book was one of the first books on human anatomy, and Copernicus's book put the sun at the center of the universe. And so sometimes people talk about that as the beginning of science. But anyway, somewhere in the late 1500s, people began doing what we now call science. And so this chapter is sort of on how we break down the motion of the planets, the people who figured that out, and how they did it. Some of the vocabulary for this section is the astronomical unit, which we've already talked about, density, the ellipse, that's a shape. You can sort of see it here in the upper right. An ellipse is kind of like a squashed circle with two things we call, each is a focus. So there are two foci or focuses to an ellipse. We'll talk about Kepler's 3 laws of planetary motion. We'll talk about the major axis of an ellipse, which is the long axis. We'll talk about Newton's 3 laws of motion and his law of universal gravitation. We'll talk about orbital period, semi-major axis, velocity, and some other things. Semi-major axis is just half of the major axis, which isn't too hard. So let's get into planetary motion a little bit. Maybe I'll switch over to the slides. I don't know if there's a better way to do this, but I'm not doing it very well right now, so I can page down. It's just a picture of the International Space Station and the culmination of our understanding of how gravity works, I guess you could say. After Copernicus's book came out in 1543, in the late 1500s, people began to explore it a little bit, and this is one guy named Tycho Brahe. He was a Danish mathematician who got interested in Copernicus's book, putting the sun at the center, and Tycho Brahe didn't buy it. He didn't agree with it. He was a Danish mathematician, and he got the king of Denmark to buy him an island in the North Sea where he stayed for 22 years, taking data. Let me see if I can skip down here a little bit and get a picture. So on the left here, this is his observatory. And what he would do is, this would be outside at night, and he would have an assistant stand in this spot and point at a star, and they would line it up and measure the angle, not a star, a planet, and they would line it up and measure the angle. And every night they would measure the positions of the planets, as many as they could see on that night, and they did that for 22 years. And Brahe thought that this would allow him to determine how the planets move. As you can see here, he lived from 1546 to 1601. As you can see in the page above, maybe there's something wrong with his nose there. He got part of his nose cut off in a duel. It was probably over a woman, but some people have said it was over, he was debating with a guy over who was the better mathematician. That seems like a great way to settle that argument. And so he was a good mathematician, and he took all this data, and he thought he was going to be able to figure out the motion of the planets from it, but he couldn't. And so he hired this guy, Johannes Kepler, who was a German mathematician, a very famous German mathematician and physicist, who lived from 1571 to 1630. By the way, Brahe finished taking that data sometime in the late 1590s and died in 1601. The story is he died of a ruptured bladder because it was impolite to excuse yourself in the presence of the king to go to the bathroom. And so that took a lot of willpower to hold it in that long. Towards the end of his life, he was trying to get Kepler to help him take this data, but Brahe was very worried about Kepler stealing his data, not for anything about Kepler. He was just worried about his legacy and all the work he had done. He didn't just want to turn it over to someone. So it took him a long time to sort of give the data over to Kepler, and then after he died, Kepler got all of the data and studied it for a few decades, I think. And Kepler was really a good scientist and a good mathematician. And in fact, when Einstein came along, many of the Germans said, we got our new Kepler. And so that was, 300 years later. So Kepler had a long legacy. So Kepler analyzed Brahe's data. And let me see if I can switch back over to I'm just not doing this very efficiently. And Kepler was able to distill Brahe's data into 3 concise laws. And this was maybe the most important single sort of set of events in the history of science. A, that Kepler took this data, and B, that Brahe took the data, and that Kepler was able to analyze it and reduce it down to a set of 3 laws. Remember, Ptolemy had a 13-volume set of books describing the motion of the planets, astronomy, and Kepler reduced it to 3 statements, how planets move. And so the first thing he figured out, or maybe the most important, was that planets move in ellipses, not circles. That was a big deal. Let me see if I can go back. Circles, ellipses, parabolas, and hyperbolas, which you might remember from your geometry class, are all called conic sections. They're parts of cones. An ellipse is just another sort of a slight variant of a circle that's been elongated or squashed. Right? The way you can draw an ellipse is just as shown in this picture, you take 2 thumbtacks and you put them into a board, and then you loop a piece of string around, and you drag with a pencil. You hold the string really taut, and you go around that circle. And what you notice is that you get an ellipse out of it, and to the extent that the string has a lot of slack, you get something that looks more like a circle. And to the extent, excuse me, that there isn't a lot of slack, you get a long ellipse, right? Notice that the taut part on the opposite side of the thumbtacks from the pencil is always the same length, is always occupying the same length of the loop of string, and so the rest of the length is the one that's reaching out from the thumbtack to the edge of the ellipse. And so the total length of that piece is always the same. And so a mathematician would say the sum of the distances from any point on the ellipse to the foci is always constant. That's the definition of an ellipse. So the long axis of the ellipse here is the major axis, and each one of these along the long axis, half of the long axis, is called the semi-major axis. It's kind of like the long radius of an ellipse, if you want to talk about it that way. And so the first one of Kepler's laws stated that the planets orbit the sun in an ellipse with the sun at one focus. So that's where the thumbtacks are. Each ellipse has 2 foci, and so the sun is at one of them. And so that was an enormous discovery. It was the first time anybody had suggested that something in the heavens might not be circles. And so, and Kepler deduced that from Brahe's data specifically on Mars. And if I drew a circle of an orbit of Mars, it would look just like a circle to you. It was a real testament to how much confidence Kepler had in Brahe's data, that he didn't just say, well, it should have been a circle, and just dismiss these differences from a circle, these tiny differences. But Kepler was able to appreciate the accuracy of Brahe's data and correctly deduce that the planets move in ellipses. So that's the first law. All planets move in ellipses with the sun at one focus. The second law, which I can just page down here, is it's called the law of equal areas. Planets sweep out equal areas in equal times. And so if it takes the same amount of time to go from 1 to 2 as it is from 3 to 4, then area A and area B will be the same. Or to say that backwards, if the area of A and the area of B are the same, then it takes the same amount of time to go from 1 to 2 as it does to go from 3 to 4. What that means is that when the planet or orbiting object is farther away, it's moving slower, and when it's closer in, it's moving faster. So that was his second law of equal areas in equal times. And the third law, which isn't written here, but I'll come to it here in a second. Let me just see if I can. Whoops. The square of the period. So the period is the time it takes the planet to make an orbit. So the period of the Earth is a year. The period of Mercury is about 88 days. The period of Venus is about 220 days. And so on. The period of Jupiter is about 12 years. For Saturn, it's 30 years, and so on. The square of the period, and the square is just the period times itself, is proportional to the cube of the semi-major axis. And so this is a relationship between the time it takes the planet to orbit and the size of its orbit. And so these were Kepler's three laws. All planets orbit the sun in an ellipse with the sun at one focus. Planets sweep out equal areas in equal times, and the square of the period is proportional to the cube of the semi-major axis. I won't ask you to do any of those calculations, but those three laws could be applied to the motion of the planets and used to predict their positions. Okay, and so now we're to Newton. Let me go back to let me do some of the dates. We said Kepler was born in 1571 and died in 1630. Galileo was born in 1564 and died in 1642. So shortly after that, after Galileo died, Newton was born. And Newton was born in England in 1643. Depending on which calendar, he was born either on Christmas Day, 1642, by the old calendar, the Julian calendar, and then in 1643 by the Gregorian calendar. But anyway, it doesn't matter. He's born around there. Right around the time Galileo died, Newton was born. And then he died in 1727. Newton had an amazing life where he made all kinds of important discoveries. Among the many is Newton put the ridges on your quarters and dimes. When he worked for the English Mint, people were filing silver and gold off of coins, off the edges of coins, and so Newton had the mint put ridges around the edges of the coins, or writing or decorations, and the government said if those are filed off, the coins have no value, and so that prevented people from filing down coins. People would file a little bit off of each coin, and then eventually accumulate a bag of gold or silver or something like that. He did many things. He invented the telescope, the reflecting telescope, which is a telescope with mirrors. But what we're going to talk about here really is Newton's laws of motion. So Newton, let me just switch back here. Newton had 3 laws of motion. I think you've heard of all of them. The first law is an object in motion remains in motion until acted on by a net external force. Newton's goal, by the way, was to develop a set of laws not just for planets like Kepler did, but for motion of all objects. This is an enormous undertaking that people have been working on for a long time, Galileo especially. This first law, that is, an object in motion remains in motion until acted on by an external force, Galileo worked on and didn't get it quite right, but Newton got it right. The second law is force equals mass times acceleration. That's just an equation. This is saying, look, something accelerates in proportion to how hard you push on it, and in inverse proportion to how much mass it has. So if you push on something really light with a big force, you get a big acceleration. But if you push on something, if you use the same force on a much bigger mass, then you get a smaller acceleration. And so just from your understanding of how fractions work, a big denominator gives you a smaller value for your fraction. You can sort of understand how Newton's second law works. And then his third law of motion is the action-reaction law. And that says forces come in equal and opposite pairs. So if you push on me, I'm pushing back on you just as hard. There's no way for you to push on me harder than I push on you. And this gave rise to a bunch of other laws, like conservation of momentum. Newton's laws did. And those are basically the laws we use to send spaceships to the moon. They're not that much changed. We plug a little more math into them, but that's the lion's share of it. It gives rise to conservation principles like conservation of momentum. For example, I think your book here. Let me just switch back to the book. Rockets work off Newton's third law, right? The rocket in this picture, whoops, hang on a second. Let me just do that right here. The rocket in this picture, this is a picture of the space shuttle taking off, but a rocket pushes fuel downward. A rocket pushes fuel downward, and the fuel pushes the rocket upward, and that's how rockets work. The rocket doesn't need to have the ground there to push on. That's not in the equation. That's not affecting the rocket at all. If this rocket were in the middle of space, we're pushing that fuel out, it would be accelerating at the same rate. It's the interaction between the fuel and the rocket inside this rocket booster that's causing the rocket to accelerate upward. Rockets are a nice example of Newton's third law. One of the things that comes from Newton's third law is conservation of momentum, and this is an example of conservation of angular momentum. You've probably all seen this. An ice skater has her arms stretched out like this. She's spinning slow. If she pulls her arms in, she spins faster. Angular momentum has to be conserved because she's on something that's slippery, and so there are no external twists on her. She's just sort of spinning there by herself, and as she pulls her arms in order to have the same momentum spinning around, she has to spin faster because her arms are in, because her mass is closer to her axis. We see this with stars, for example, as they age and collapse. Even though when they're big, they're spinning slow. As they get more compact, they'll spin faster and faster. Here are astronauts experiencing weightlessness. Weightlessness, if you noticed here, is put in quotes because technically they're not weightless. Weight has to do with gravity. And so astronauts on the space shuttle up above the Earth or on the space station are still experiencing gravity. That's why they're going around the planet in a circle. But they feel weightless because there's no other forces acting on them. It's the way you would feel weightless if you jumped out of an airplane. Gravity is still acting on you. It's the thing that's causing you to fall. So here's the orbits of some objects around the Earth. Notice here's Jupiter, and then you can see Mars and Earth and Venus and Mercury and so on. And if you notice the planetary orbits, those are the black lines, I think. They look pretty circular. Some of them you can see aren't quite circular, but they look pretty circular. When you look at other objects like these blue ones, which are asteroids, or the red ones, which are comets, they're much less circular. And those are just smaller, odd objects. Most of the planets are in circular or nearly circular orbits. It's just what happens when you have fairly large mass objects interacting over long periods of time. So Newton was trying to figure out, after he figured out his three laws of motion that we just talked about, he wanted to figure out how gravity worked. And so he imagined, the one on the right is actually a drawing from Newton. He imagined if you get on top of a mountain and shoot a cannonball just slowly, it will just arc to the ground, and if you shoot it harder and harder, it will reach further and further around the Earth until finally it goes all the way around and hits the back of the cannon. Same thing with the person on the left is throwing a ball with a greater and greater velocity. Eventually, in principle at least, you could throw it hard enough that it came all the way back around. That's really only feasible if you have some rocket launcher in space or something like that, but the idea is correct. We now have lots of objects that are orbiting the Earth. These are all debris and other objects that are being tracked by NASA. The scale is wrong on these pictures, so it wouldn't look like that if you were actually looking at it. Let me just pull the So we're going to talk just a little bit about mass here for a minute. So you probably have some experience. Mass is how much stuff is there. It's different from weight. Weight is mass times gravity. And so we have words like mass and volume. Volume is how much space an object occupies. Density is mass divided by volume. And so if you have something that has a low density, then you have to have a large volume of it to have much mass. So styrofoam or pillows, they have a low density because they're mass divided. They have a large volume compared to their mass. Lead, gold, metals, they have a high density. They have a large amount of mass and a small volume. And so density is just the mass divided by volume. So Newton's law of universal gravitation is this. And I'll just talk you through it just a little bit. The force of gravity between two objects, we'll call them M1 and M2, these are two masses, is G, which is just a gravitational constant, a constant of the universe, times the product of the two masses divided by the distance between them squared. And so mass 1 times mass 2 divided by the distance between them. And D is really just, hang on a second. Get back over here. Okay, we talked about density. So here's Newton's law of universal gravitation. There's a whole story behind this. He discovered this in 1687. It was one of the big achievements of his life to come up with this equation for describing the force of gravity and showing that it would actually work. He had to show that a force like this would produce orbits that are elliptical. That was the challenge, one of the big challenges Newton faced. And there were other guys around at the time who were sort of participating in this discussion. And so the gravitational force is this universal constant called G, which is just the gravitational force constant. M1 and M2 is the product of the two masses that we're talking about. So the force of gravity between any two objects is proportional to the product of their masses, m1 times m2, divided by the square of the distance between them. So you say divided by d squared. And so you notice as d gets larger, the force has to get weaker, right? As the objects are moved farther and farther apart, the force between them gets smaller and smaller because you're dividing by the square of the distance to get the force. So let's talk a little bit. I'll have another little video for this, but let's talk just a little bit about this. Turns out all planets, so the motion of the planets, we've already said they all move in ellipses. They look like circles. They look very close to circles, but they're not. They're ellipses. And they all orbit around the sun in approximately the same plane, not exactly, but approximately all in the same plane. They orbit all in the same direction. That is to say, if you're looking down, maybe they're all going counterclockwise or something like that, depending on what you call the top and the bottom of the solar system. Comets do this as well, and asteroids, but not as sort of neatly as the planets do. You can have asteroids that are more tilted out of the plane of the solar system, and not have nearly as circular orbits. And comets, depending on how far out they are can be way out of the plane and way elliptical, extremely elliptical. So that's a little bit about the shapes of the orbits. We'll talk about, as we talk about planets, that we'll talk about two types of planets: the large Jovian planets, which are Jupiter, Saturn, Uranus, and Neptune. And we'll talk about the small terrestrial planets, Mercury, Venus, Earth, and Mars. And then we'll talk about sort of small objects, the inner objects, which are the asteroids, which are mostly between Mars and Jupiter. And we'll talk about the small outer objects, which are comets. And then we'll talk a little bit about dwarf planets and what happened to Pluto, but we'll do that as we get to it. So for most of history, the main planets known through all civilizations were Mercury, Venus, Earth, of course, Mars, Jupiter, and Saturn. Uranus and Neptune are large planets, but they were so far out people hadn't realized that they were planets. Nobody had seen them until telescopes were invented, and even then it was a while before they were found. Uranus was discovered in the 1700s by William Herschel and his sister, and there were irregularities in its motion. It wasn't quite obeying Kepler's laws or now Newton's laws the way they expected it to. And so there were a few people, one of them this guy Leverrier, who, and John Couch Adams was the other one, who suggested there could be yet another planet besides Uranus whose presence was causing Uranus to not quite be where it was predicted to be by Newton's laws or Kepler's laws. And that's how Neptune was discovered. Both Leverrier and John Couch Adams suggested that an eighth planet might exist, causing this erratic or unexpected motion of Uranus. And they got observers to look for it, and sure enough, they found Neptune. And so that's how Neptune was found. This was a huge victory. This happened in the 1800s, and it was a huge victory for Newton, who was long dead, because people thought that his laws might not be completely correct. But in fact, they were used, Newton's laws were used to find the position of Neptune based on how Uranus was moving. And so it was a big confirmation of Newton's laws. Let me go back to the pictures now here for a second. There we go. These are just some of the computers that track all of the objects orbiting the Earth. It's scary how many things are up there. These are pictures of John Couch Adams and Urbain Le Verrier in the 1800s, both of whom are credited with having discovered Neptune using Newton's laws.